Welcome back. This is Parametric Equations Part 3, and if I haven't already, I will post this PDF on Blackboard. Okay, this is the example part. Parametric Equations Intro was the theory. Part 2 was the changing from parametric to rectangular mode, vice versa. We did the interesting problem of the ellipse and talked about speed and omega and interesting. Now, this is an example. The topic is projectile motion. Projectile is anything which is launched. It could be it could be a baseball, it could be a golf ball, it could be an arrow from a bow and arrow, it could be something thrown. It would not be something which has a built-in motor. It will be something which does not have a motor in it. It's something, as I said, which is thrown, a baseball, a rock, a spear, a bow and arrow. It has an initial velocity, but it doesn't have a motor in it, so that what's acting on it is gravity, which is pulling it to Earth. Okay? All right, so let's talk about that. Parametric equations of projectile motion. All right, so we have a little diagram here. We have our parametric equations, which I will attempt to explain in great detail. And okay, so let me see. All right, first of all, let's go back to the idea of vectors and components. Okay, we have a velocity vector right here, which is, well, I guess we're actually talking about the magnitude, but something is thrown, fired, tossed, hit at an angle theta. And of course, we have our vertical component and we have our horizontal component. Now, we've seen this in the past, right? The horizontal over the resultant is cosine, and the vertical over the resultant is sine. So we manipulate that a little bit, and this would be V0 sine theta is our vertical component, and V0 cosine theta is our horizontal component. So let's go back and look at our parametric equations. Okay, so we have them broken down into a horizontal component, that's the x component, and the y component. So this is very similar to what we dealt with in vectors. Okay, now x is a distance, and what we appear here is a rate and a time. And you know distance equals rate times time. So that's where the justification comes from. So the horizontal position is the horizontal component of the velocity times the time. And the vertical component, or the vertical height, is based on three items. Let's talk about these step by step. First, we have the initial height that the object was tossed, thrown, or fired from. So whether it's a bullet or a bow and arrow or a spear, or a baseball or a golf ball, if the initial height is h, we have to add that. And I hope you can see this diagram is this part of the more general diagram. All right, so first off, if we're talking about the y value, it's the vertical, and that is dependent upon the initial height that we start at. It's also dependent on rate times time is distance, right? So this is the vertical component of the velocity times the time. So this gives us the vertical height due to the initial velocity, okay? And then what's acting on the vertical is gravity. So you may have learned in physics class that the distance s equals 1/2 at squared. Okay, well that's what this is. Negative because gravity acts downward. G is used for the acceleration due to gravity. So this is negative 1/2 AT squared, which is a distance, right? You learned in physics S equals 1/2 AT squared. Okay, so now let's go ahead, and all these three items affect the vertical position or the height of a particle. Gravity is pulling it down. We have the vertical component due to the initial velocity, and we have the height from which an object was initially thrown or tossed or fired. Okay, and this applies to footballs and golf balls and baseballs and bows and arrows and rocks and bullets, things of this type. Okay, so we have a lot of variables here, so let's constants as well. So let's go ahead and let's list these. V0 is the initial velocity, that's a constant. Right? If this doesn't have a rocket engine to it or a jet engine to it, the initial velocity is going to be pulled down by gravity. Okay, theta is the angle with the horizontal. G is a downward acceleration due to gravity on the surface of the Earth. It's 32 feet per second, or 32 feet per second squared. Since gravity acts downward, hence we have the negative here. Okay? H is the initial height as we saw. V sub 0 cosine theta is the initial component of the velocity. V0 sine theta is the vertical component of the velocity. All right, so with all that taken into account, so this is the parametric equations, or these are the parametric equations for projectile motions. So let's go ahead and let's do an example. Okay, and this example is right out of our textbook, so you can follow it along, or I'm going to post this up on Blackboard and then you can follow it as well. Suppose Jim hit a golf ball with initial velocity of 150 feet per second at an angle of 45 degrees to the horizontal. Okay, so we're going to do some various things here. Step 1, or part A. Find the parametric equations that describe the position of the ball as a function of time. Okay, position of the ball is going to mean its position horizontally, which is the x, and its position or height vertically, which is the y. So let's just go back and look at the story. There are certain givens here in the story. First off, v sub 0, the initial velocity, is 150 feet per second. The angle is 45 degrees. The initial height is 0, it isn't mentioned, but since he's hitting it from the ground as opposed to standing on top of a hill, h equals 0. And g, acceleration due to gravity, is 32 feet per second squared. Normally in a lot of textbooks there's a negative in front, but let's not forget the negative is already here. Okay, so we're not going to worry about that. We're just going to know that gravity acts downward. Okay, so here we go. Let's get our formulas. X is V0 cosine theta times the time. Again, this is the horizontal component of the velocity. This is time. So rate or velocity times time equals distance. This is horizontal, and this, of course, is the vertical. So let's put these in. V sub 0 is 150. Cosine theta is cosine 45. Cosine 45 is rad 2 over 2. You get 150 times rad 2 over 2. That's 75 rad 2 over 2t. So this is the x component, or the horizontal position of the golf ball at time t. And try and understand that this t is not under the radical. You have to be a little careful about that. Maybe I should have put an extra little space here. You may want to do that. Okay, so we're using the fact that sine of 45, cosine of 45, and both rad 2 over 2. Okay, so let's work with our formula for the y value. I should have had a negative here, but I'm going to put that in when I upload this, so make sure that that's there. So we have three parts. Okay, we have the negative 1 of gt squared plus v0 sine theta t plus h. So, okay, let's put the numbers in. G is 32, acceleration due to gravity on planet Earth. If you're on Mars, it's less. You're on Moon, it's less. The gravitational attraction is less. And sine of 45, of course, is rad 2 over 2. H is 0 because Jim is standing at ground level. The golf ball starts at ground level. Okay, so working this out, this is negative 16t squared. This is rad 2 over 2 plus 75 radical 2t. So these are the equations. This is the horizontal position at time t, and this is the y, or the vertical displacement or position at time t. Okay, so now let's answer some questions. Part B, how long was the golf ball in the air? Well, this is one of those duh moments. The golf ball is in the air until it hits the ground. Well, what's true on the ground? Now, sometimes when I do this in calculus, students will say, well, velocity is 0. And I say, oh, well, that's not true. So I stand on the chair and I tell them I'm going to drop a book on their head. And if they feel something, the velocity wasn't 0. And they laugh a little bit, but that's true. The idea is a golf ball is in the air until it hits the ground. The question is, when does it hit the ground? Well, it hits the ground when y equals 0. So what that means is, for this question, we're going to set the y value right here equal to 0. And this is like a quadratic, so we factor. And we get t equals 0. And then we get this quantity, if we factor this, is also 0. And we move over to 16t divided by 16, we get this value. So we have 2 times when the golf ball is at height 0. One is t equals 0, which of course is when it's first hit. At that moment, before it's instant before it's hit, its y value, its height is 0. And then it's going to hit 0 again. You work this out, 6.629 approximate seconds. Now, notice the symbol here, this is approximate. If you put an equal sign, it's wrong. I mean, we're rounding off to 3 decimal places here. In actuality, it's a bit more complicated than that. Okay, part C. When was the ball at its maximum height? And then also determine what is that maximum height. So when is sort of a giveaway. It says find t. So at what time is the ball at a maximum height? Now, maximum height occurs when the y component of the velocity equals 0. That's correct. Now, normally we can't find out that unless we use calculus, and this is not a calculus class. You see, because obviously, let's think about this. Velocity is a continuous function. On the way up, the velocity is positive. On the way down, the velocity is negative. So it must have been 0 at that peak. So that's what that deals with there, but we don't know how to find that yet. That will be calculus. However, one thing that we can do here is we can realize this is a quadratic. And only because it's a quadratic, I guess we could also do it on a calculator. That's a little more involved. But since this is a quadratic, we have an axis of symmetry, and the height, because it's concave down, right? Because the coefficient of the y is negative here. It's concave down, it has a maximum. Okay, so what we're going to do is negative b over 2a. We normally write that x equals negative b over 2a. That would be the axis of symmetry. That's the x value that gives us the maximum or the minimum. But in this case, we're using the variable we're using is time. So by solving this, this is going to give us the time in seconds that it reaches the maximum, which is going to answer the when part of this question. So a is negative 16, b is the coefficient of the t, it's 75 radical 2. So it's b over 2a with a negative in front, okay? So the negatives cancel, and you're going to work out 75 radical 2 over 32, so you get 3.315 seconds approximately. Again, this is an approximation. Notice I'm not using an equal sign here. If you use an equal sign, it's technically incorrect. So if the question asks what's the exact, then you would just give me 75 rad 2 over 32. That would be exact. Once you put this in your calculator, it's an approximation, and the usual standard is 3 decimal places. So if you're not told the level of rounding to use or the level of accuracy, we typically go with the 3 decimal places. Okay, so this is the number of seconds approximately rounded that the golf ball in this case, will be in the air. The maximum height, or rather I take that back, this is the number of seconds that it takes to reach the max, okay? Because the maximum height occurs on the axis of symmetry. Okay, now what is the maximum height? Well, we now know t. So the maximum height, we can go back to our y function, okay, and we can plug in. And the y function, of course, is right here. And we're going to plug in t is this crazy value. Now, we don't want to plug in 3.315 because that's rounded. And if we did that, we're using a rounded value to do a computation that will compound the error. And you'll learn about that in calculus, how that works. It's called differential. So the rule of thumb is we're going to use the exact value. And exact is, well, let's call it 75 rad 2 over 32. You can put that into your machine and plug in, or you can use the value that the calculator has, understanding that these dots mean that there's more. So if I put that in, you get negative 16t squared. We're using this value of t that the calculator received, plus 75 radical 2 times t. Again, we're using this value that the calculator used. We're going to get 175.78125, round to 3 decimal places, so 175.781 feet, because a y value is a distance. The distance here, according to the units, measured in feet. Time is in seconds, distance here is in feet. So that would be the maximum height the golf ball will reach. Okay, last part, determine the distance the ball traveled. Well, once again, it's going to travel until the y value equals 0. And the y value equals 0, we computed the time right here. T is approximately 6.629 seconds, or this is the exact value, okay? And what we're going to do is going to put that in our calculator. And again, we're going to use this value with the dot, 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 because this is the value that the calculator had. We're going to call this exact because we got the dots on the end. You leave off the dots, not really exact, it's rounded. Or you can use, 75 rad 2 over 16 and plug that in here, and that will work out fine as well. But at any rate, you put this in your calculator, you got X max, approximately 703.125 feet. Again, this means approximate. Okay, so the only issue I want to go over with you here is the question of rounding. Note, it is most accurate to use exact values in all computations, which means we do not want to use rounded values, because then in subsequent computations the errors accumulate, okay, and they really do. All right, so the general rule is you round last. So that's the reason why I made a big deal about using this here with the dots on the end. The calculator even has more values stored which we don't see. In this case, it's got 10 digits stored, but there are more that you don't see. So we're going to use the most accurate values as we can. And notice if you use the 6.629, which is the rounded result from earlier, you might want to put this in your calculator, multiply by 75 rad 2, and how much ever we were off by, which is 0.000126074 dot dot dot, is going to be multiplied by this amount. It's going to have an effect. It's going to change your possibly the thousandths place, maybe more. So if you want the most accurate result, you use exact values, and your rounding, if you do it at all, it should always be last. Okay, so I'm going to put this up on Blackboard, And I will make that one correction we talked about. I forget where it was exactly. Yes, I want to have a negative right here. Okay, so I'll take care of that, put it up on Blackboard, and I hope the video helps you. And we now have finished chapter 11. So the parametric equations problem set take home will be the last one in chapter 11. So chapter 11 then will be composed of, I think we had the parabola, ellipse, hyperbola, rotation of axes, and this one, which will be 5 of them, will be totaled, and that will be your chapter 11 grade. And then we move into chapter 12, and we'll have some fun with systems of equations and matrices and Cramer's rule and things of that type. Okay, so have a good evening, and hope this finds you well.